So today, and I'm here basically to talk about the role of algorithms in everyday life. What you're watching here is actually a very famous match. This is Dwarf Scout versus Little Factory. This is a 1994 Grandmasters tournament. This is it in progress, and this is basically, this is it. Like, this is as exciting as it gets. It's not a popular game. There's really nothing to do after you write an algorithm and let it loose except just watch it win or lose. So I'm here to talk about sort of where these algorithms came from and where they're going, where they should go, where they could go, and where Homo sapiens, where people fit into all of this. And to sort of more broadly, to talk about what AI is, which people talk about a lot, with not a lot of precision, but let's say human intelligence as exhibited by machines. And I think the overall crux of what I'll be talking about today is that it's kind of a dark road that we're going down relative to AI and machine learning. And to talk about what an alternative to that dark road might look like, and how there are indeed some people who are trying to build an alternative. And back where I'm from, at MIT and a couple of other places, we don't talk about AI that much in a way. We talk about machine learning, we talk about deep learning, but when it comes to intelligence, there's actually a different way to go. And I think it's a reasonable impulse to seek it out and build it. And if you're looking to optimize any lines of business at all, or if you're an engineer who's looking to prove themselves in any way, the appeal of building these kinds of technologies is kind of irresistible. So it starts here in Holland in the 30s. So this is a machine that was developed in Holland in the 30s, and it's a machine that's designed to listen to the air. Okay? And so what the Dutch were trying to do was they were trying to hear airplanes before they arrived. They knew from the First World War that if you could understand that an airplane was coming long before it got there, you could take all kinds of precautions and so on and so forth. And the notion of this, the idea of being able to understand the information before it hits you, became very valuable. So this is sort of the very first prototype, and then it became sort of personal. And this is a weird picture. It's a weird picture. Somebody has combed their hair before they put this thing on. The impulse is a little bit weird, and it's kind of, it's a funny picture, but it's obviously serious stuff, because this is what they were listening for, right? Like what they were, the one thing that they were trying to do, what we all want to do, is to basically receive information before the information becomes action, right? Basically, to know what's going to happen before it happens to us. And that's everything, right? Like that's what it's all about. And it's a very human urge. It's sort of the quintessential human urge from the minute that we planted crops and the minute that airplanes hit the sky and democratic elections and football games. We just want to know what is going to happen. I think that there's sort of three important technological shifts basically in the 20th century that make this possible. The first one is radar, to be able to see the future a little bit, computation to be able to model the future a little bit, and then finally machine intelligence to be able to predict it. And this notion that now we have machine intelligence, now we have AI, and we can predict the future, now we can predict the future for real, and we have made it through the AI winter. The AI winter refers to the period, so AI is sort of conceived in around 1956, and billions and billions of dollars go into it, and it just craters. It craters basically through to the 80s, and a huge amount of money is wasted, in part because the notion of what we were building, it turns out, is either impossible or nowhere near possible yet. And that idea was that we could somehow train a computer to think the way we think. And all we have to do that is, first of all, figure out how we think, which, we're not really that close to that. And the efforts in which we said, okay, all we need to do is to train machines to see the way we see. Well, first we just need to understand how we see, or how we hear, how we understand language, how we produce language. And it was actually kind of a catastrophe. And it's really only the advent of machine learning that starts basically in the 80s, and really deep learning that comes later. And I think it's important to sort of understand that what makes deep learning possible is basically two things. So machine learning starts out, but the two things that really turn it into what we have now, which is something very sophisticated, there's no question, there's no doubt. But what makes that possible are basically two things. So one is just computational power, raw computational power, and that's the basics of Moore's law, that just we can crunch a lot more numbers a lot faster and so on and so forth. But the other part of it is really what the internet did as a strange byproduct of its connectivity, which is to produce data sets that are without any notion of precedence in human history, right? Which is to say, all of a sudden we have billions of faces that are accessible to train machine learning on faces. All of a sudden we have billions of locations to train location data on, and so on and so forth. That suddenly there were ways to get the amount of data in to produce meaningful output out of the neural networks that are being built. And all of this has given us sort of unprecedented superpowers as a species, that by using these machines with enough data, we can effectively predict the future, which is why nothing will ever surprise us again. This is the night of the 2016 election in the United States, where the most sophisticated data analysts using the most sophisticated data explained how this was going to be a victory for Hillary Clinton. This is up until about an hour or so before the actual data, final data came in and said otherwise. That's why nothing will ever surprise us again. There's this notion from that's sort of populated and propagated and really reinforced over and over and over again. Chris Anderson gave it words. He used to be the editor of Wired magazine. That with enough data, the numbers speak for themselves. That all you really need to produce some valuable outcome is just enough data. And not intentionally or specifically, Chris is articulating a statistical approach to AI, right? As opposed to where things started, which is trying to build systems that used reason or logic. This is a purely statistical approach. And it's the statistical approach that brought AI out of the AI winter into the sort of multi-billion-dollar dreams that we see today. But these intelligent machines, they could have gone either way. And this is actually the original idea was to get machines to think, to use symbolic reasoning, you know, this is a sort of weird hybrid of the two. This is actually using machine intelligence to try to map what's called the connectome, the neurons in the human brain. This is actually the eye, but effectively the brain. And the notion that we don't really need to understand how the brain works. In fact, we can use purely statistical data just to even understand how the brain works, right? That, like, the brain can't understand how the brain works. And at the core of this is this notion that if we can just get enough numbers, enough data, enough signals, it will yield, it will break, and we will understand. And you know, the benefits of a purely statistical approach, they're evident just by looking at the great gains in the efficiency and stability of financial markets, which, after all, right, let's think about it, like financial markets, unlike any other form of data, are just data. That's all they are, right? You're not trying to extrapolate something from something else. It's just a bunch of numbers that are moving around, and in a closed ecosystem. And in a way, you know, that's what makes them sort of the avant-garde of automated decision making. So I would say that of all of the many areas in which automation and in which machine intelligence were applied, financial markets got it first. They got it the best. They have it the hardest. And a lot of what will play out in all of our lives in a million ways, you can see it having played out and continuing to play out in financial markets themselves. So this is basically the rise over time of automation in trading on the stock market. You can see it. It starts slowly and then becomes sort of like a forest fire until it becomes basically 70% of all trades on the global market. Such that when there is a crash, as there was a couple months ago, about 6 months ago, this is what it looks like. The sad photo of Wall Street traders reacting as the stock market plunges, right? There's no, right, like the notion that there's any human engagement or involvement on a gain or a loss is obviously laughable. And all of this is obviously better, right? Because the alternative to that, like how things used to go, is an obviously terrible idea. This is obviously a terrible way to move information around, which is how we moved information around for, let's say, 500 years, maybe about 700 years. And the notion of setting out to replace this with something that machines can engage and automate and understand with precision, it's an obviously it's an obvious move, right? You'd be bananas. Even like a tic-tac-toe playing chicken could look at this and say, this is not how you want it to go. And this is true not just for the stock market, but for anything, right? Like this is, when I worked in advertising, this is what a media buy looked like, more or less, kind of, right? But what you see is that there is an alternative to this, but that alternative, which is exemplified in, among other things, something called the Better Alternative Trading System. This is a trading system that's used for 11% of the stock market. Its nickname is BATS, not a good name for a stock trading system, by the way. They're responsible for 11% of all US trades, and they went to do an IPO on their own platform. Okay, so these are the guys that really automate all the trading, and they set out to do an IPO on their own automated platform, and it caused every stock that began with the letter A and B to crash somewhere between 10 and 50% in about a minute and a half, such that their own stock actually went from $16 to a tenth of a penny in 1.5 seconds. And this is the stock of the company that makes the platform that it's being traded on. And the unnerving thing about that is that when that happened, when it went from $16 to a tenth of a penny in 1.5 seconds, there wasn't consensus. And even for a long time afterwards, there wasn't consensus over whether that was a feature or a bug, whether that was some kind of problem that was sort of like in the code of the software, or whether that was a deliberate attack on the company that makes the software. And the scariest thing about that particular software and that particular effect is that the software that did that is still online. That's still running the whole mess. That's still running 11% of what we're doing globally. And that's just one of 18,000 algorithm-based crashes in the stock market over a span of 5 years. Some of them are huge, some of them are tiny, but 18,000 of them over 5 years. And this is what I'm afraid of, right? Which is not that machines are going to somehow become sentient and powerful, but rather that they're going to be dumb and fragile. Because if this is what billions on the stock market look like, right? If this is what billions on the stock market look like, you can just imagine what your DSP trafficking systems are up to. So without any idea of what's in the black box, basically the numbers that speak for themselves have become numbers that speak to themselves. And what happens is you have people who are listening to the wrong numbers, and then you have numbers who are listening to the wrong people. Because even though we've built them, we don't actually know how they work. And honestly, this is not a talk about financial markets, because it would just be a finance story of 18,000 crashes if only these answers without explanations stopped there. But really, they support a lot more than the stock market. This is a structural node by the engineering firm Arup on the left, and that's designed by an engineer. And this is basically to hold up cables that hold up a building like this one, and that is basically how an engineer would approach it. And it's a perfectly good approach. Uses a bunch of metal. You can see it's a bit imprecise. So be it. If you feed the same criteria to a machine and say, look, never mind what we don't have any preconceived notions of what it should look like. We don't have any preconceived notions of how it should get made. If you needed to hold up this much weight with, under these conditions and so on and so forth, what would a machine come up with? And what the machine came up with is that on the right. And that thing on the right actually does a way better job than the one on the left. Like a way better job. And it uses a lot less metal. And it's way more precise. But there's no way to understand its logic because it doesn't come from a human. There's no if and when that fails, which is inevitable, how will we understand how it failed? Because it doesn't present itself. It's trying to understand the logic of what's on the right. It's like trying to understand the logic of a dandelion or an octopus, right? Like everything about it exists for a reason, but that reason has more to do with evolution than intention. And so this is just a few minutes of computation. It's just as elegant and just as inexplicable as the dandelion and as the octopus. And this link between the notion of evolution and computation is what's led to the notion of a specific type of algorithmic approach, which is called a GA, a genetic algorithm. How many people are familiar with that notion? Curiosity. Okay, so there's a good way to get your head around it. A genetic algorithm, you know, a lot of times I think when people imagine what an algorithm is like and as it's applied to everything, which includes all the media that you're buying, everything that happens online, everything that touches you in every part of your life, you imagine that somebody's got some idea about how it should go. And in reality, it's much closer to what you see here. So this is a genetic algorithm that says, look, you have this much mass, and you have between 1 and 3 wheels, and you just need to get the object from the left side of the screen to the right side of the screen in this simulated environment. We have absolutely no idea. We are not giving you, the machine, any ideas about that the wheels should be on the bottom, for example. A perfectly obvious notion, but it's got to try it out. So it tries it out. And it tries all of these out, and it goes through one cohort, does 15 of these, finds one that performs a little bit better, and says, okay, with that one, I'm going to mutate that 15 times. It basically does what nature does, right? Which is to say, whatever the one that is most fit, take that one, reproduce it with a bunch of mutations, pick the one that's most fit, reproduce that with 15 mutations, and you give this particular machine about, I don't know, an hour on a laptop, and you get to here. And the thing about this is that there's never been any instruction that says you probably want big wheels because it's a bumpy road. You probably want 2 wheels because 1 wheel's never going to work, 3 wheels never going to work. None of those things are baked in. Those things are arrived at through the same processes that we all arrived here, basically, which is through genetic mutation. And you know, I can watch this for hours, right? Because it's sort of like, you know, going back to that first one, it's like watching a puppy in the snow. You know, it's sort of fun to watch a machine fail, but it's sort of delicious and maybe a little bit scary to see how a machine can arrive at something that we would just call intuitive. Right? But it's not intuitive because the machine could also never explain why that's better. And sort of this is what's holding us up at this point in every possible way. This is how we end up here. So if people are afraid of an AI that knows too much, that's not the fear to have, right? The fear is of humans knowing too little about the world that we've made around us. This is a building that is in Endesa, Spain, where it is optimized for to produce all of its own electricity through solar gain. So every angle of that is optimized for exactly where the sun is at that particular latitude and longitude in Spain, and that's all brilliant. It's great, and there's actually some very complex algorithmic work that goes into that. But you know how this is going to end, right? Which is that somebody's going to build something next to it, and all of that is shot, right? Because this is the problem with all the systems that we build, is that we build them for everything up to the moment that we've built them, right? We train them on the history of everything up until the moment that they become useful. And from that moment on, they actually lose their utility because the system is producing things that it has never produced before, whether that's a new building or what have you. And you know, this has consequences, right? If you can't explain it, and if you can't defend it or address it, you can't fix it. If you can't explain it, you can't fix it. And the world sort of becomes increasingly efficient, but also increasingly fragile. This is the great flu crash of 2013. This is when Google was looking at search signals. Now, who has better information about who is searching for what for flu symptoms than the largest search engine on the planet? So they are getting all these signals to the point that they can start to reasonably predict where and when the flu is going to hit, which is amazing and incredibly useful. And in fact, the Center for Disease Control in the United States actually shifts their practices so that they can start using, they start to throw away the sensors that they were using, which is basically like talking to doctors, so that they can capture this incredibly efficient means by which we can understand what people are suffering from around the world. And that works right up until the point that it doesn't, which is 2013. It's now 6 years ago. And the whole thing has to be sort of pulled down and just put in the ground because nobody could explain exactly why it failed. They just knew that it was working and then it wasn't working anymore. And this is the snow crash in 2015. So this is when, in New York City, an enormous snowstorm was predicted that was going to shut the whole city down. And so it was in 2015 that for that snowstorm, they actually took down all the subways, which never happens in New York City. Like, just nobody could go anywhere. They canceled all the big shows. A couple $2 billion in revenue disappeared, and then, I don't know, maybe like 3 inches of snow came in. And it was an economic catastrophe. And the question is, like, you know, big data, and we can't even figure out if it's going to snow. All right, why not? Why not? And the reason is because there are actually many different models of the weather, right? There's all of these different models of the weather, and you can see that they differ somewhat from one another. But only one of them has outperformed all the others over a period of about 20 years. It's called the Euro-Next model. So there's all these different ideas of what the weather might be, but only one of them is basically right all the time. It's called the Euro-Next model. And so the Euro-Next model said it was going to be this cataclysmic snowstorm, and so everybody looked at that and said, okay, it's going to be a cataclysmic snowstorm, shut the city down, and that's exactly what they did. The problem is that if they had looked at all of the other weather models, all of the other weather models were saying otherwise. And what any rational and reasonable person would have done if we were trained to look at data this way, which we're not, but what any rational and reasonable person would have done is look at the model that was performing well in relationship to all the other models and try to understand, why are they different? These are different, why are they different? Not which one is not, rather than asking which one is right, asking why are they different and what can we figure out from that. And part of the problem is that we're not trained to look like that, and then part of the problem is the sort of data diet. This was a very well-intentioned notion it's about 4 or 5 years ago. The idea, well, look, everybody who's driving, and this is 5 years ago, so this is when smartphone penetration wasn't quite as high as it wasn't nearly as high as it is now. So you're with your smartphone in your car, and it's got sensors in it, and so we'll be able to detect where all the potholes are, right? Because the sensors can tell you that the car is bumpy there, and we'll just track all that, and then the city can use that data to figure out which streets to fix. What's the problem here? The problem here is that people in some neighborhoods had the phones that could do that, and the people in other neighborhoods didn't have the phones that could do that. And guess who actually needs more help from the city? Right? And so the problem is that we produced a data set that was implicitly and explicitly biased towards a specific subset of the population without understanding that that's what we'd done. And overall, this is sort of the trend across I think every industry that I know of, that I've ever worked with, which is not understanding that there is no such thing as a crystal ball. There's just a bunch of signals that you're gathering, and where you gather those signals from is the single most important thing. Everything else is just math. This is a great story, which I guess we don't really have time to do, so we won't do it. But anyway, it's an entertaining story. The problems with creating this isn't just that they're wrong. The problem is that they're wrong and they're vulnerable. And when they're vulnerable, it means that they can be exploited. And exploitation is everything from ad fraud to car crashes. Everything from military risks to information security risks to what have you. This is Josh Brown, who was talking about it relative to the stock markets, but I think it's important to understand that creating an infrastructure in which all vision and information has an automated output makes it exploitable in ways that we could never imagine across the board. This is Adam Harvey, who's an artist in New York City. who went deep into the stack for facial recognition. And again, at this point, by now, in 2019, there's no human alive who can explain exactly how the facial recognition algorithms in your phone work. But you can reverse engineer them. You can basically work to spoof them. And Adam basically arrived at a makeup technique, if you can call it that, that will, this person does not have a face as far as any computer is concerned, right? This is a ghost in the contemporary landscape. And you'll see this across every aspect of society. This is here. So this is Epigotrix is a script evaluation company out in Hollywood, and basically when the studios are trying to put a value on how much is a movie going to make, they'll say, well, is it a $5 million movie or a $50 million movie, whatever. They'll just run the script through the algorithm to figure out whether it's going to work, because they've got 100 years of cinema to look back at, and they can see what's happening where. And so it is that in script writing forums, there are script writers who are trying to figure out, well, what is the algorithm looking for? Like what can we do? And so they're no longer thinking, well, what is the trend, or who is the person who might, they're looking for the vulnerability in that system. And this will sort of replicate every place it can. This, I don't know how many people remember when this happened, when there were, this is in 2013, this is when there were 2 explosions in the White House and Barack Obama was injured. Nobody remembers it because it never happened. It got the Associated Press tweeted this because they got hacked, and not that many people actually engaged with it. 483 retweets, not a lot for the Associated Press. The Associated Press realized it about 2 minutes later, pulled the whole thing down. But meanwhile, that's what happened to the stock market. And I think, I have to look at the numbers, I think it was a couple, I don't have it in front of me, it's a couple $1 billion in value that disappeared. Why? If nobody believed it, and everybody knew that this is not a real story because it's easy to check, why did that happen? It's because the whole stock market is predicated on a whole bunch of signals that include the semantic parsing of what is happening on social media. Right? So and by the way, do you know who's responsible for this? Anybody know? This is the claimed and direct and acknowledged work of the Syrian Electronic Army in 2013, which is basically the cyber division of the pro-Assad Syrian forces, who set out to destroy a couple $1 billion of value in the stock market, and did it. And all they had to do was figure out the AP password. The reality is that in a robot-readable world with machine legibility, when we change who we write for, which is to say writing for the machine, it changes what and how we write. This is basically the best thing that a human has done, in my view, over the last 50 years. This is in Poland, a car. In Poland, they removed all the traffic police because you can replace them with cameras, right? You're just looking for people who are speeding or going through red lights. We'll put cameras up that just read the license plate of anybody moving over a certain speed or going through a red light, which is fine until the license plate has what's called a SQL injection hack as code written into it, okay? So basically, the code in this license plate alters the database of any camera that reads it. Good job, humans, right? It's amazing. It's really one of the most beautiful things. And, you know, I think, like, it's real, it's also funny, but this is what our future looks like. This is what our future looks like. This is the work of James Bridle, who's an artist who set out to trap his car. This is a self-driving car that will never go anywhere. It's like a magic trick, right? You know, it's just in chalk, but that's it. That car's going nowhere until somebody erases that chalk. And, you know, this is what, you know, we would say like an adversarial engagement, right? Like this is like basically like okay, the machine is looking like this and I'm gonna do this. And here's the gag about the adversarial approach, right? That even the notion that the machine is looking at the world one way and we humans are looking at this other way, even that can be extrapolated up into the machine layer. And it generates something called generative adversarial networks, GANs. Has that phrase reached anybody here yet? Okay, it will. So GANs are basically a practice that says that the best way to figure out what the optimal results are isn't just to have a bunch of signals and have a machine that's trying to figure that out. It's to actually have a machine that's generating a bunch of signals, trying to fool another machine, and that machine is trying not to be fooled by this machine. And you basically put those two into conflict. I'll skip over. Well, okay, yeah. So this is 7 years ago. This is 7 years ago, and there's one called an algorithm that's just generating random pixels. And then there's another algorithm that is just looking for faces. That's all it's doing, it's looking for faces. We don't really know how it looks for faces, but that's what it does. And you basically put those two together, and these are all the ones that pass the test, right? And you can, like, this is what a machine thinks a face looks like. But you fast forward 7 years later, and this is what GANs are doing now. So that's 3 days of work. So these people don't exist, have never existed. These are being generated by the same way that car was generated that I showed you earlier, right? That little car moving across the thing, right? Same idea. It's just that the criterion is not can it make it from A to B, but rather does it look like a face? And the more you tune that one that's looking for the face and say like, no, I want you to be really, really careful. Does it look like a face now? Does it look like a face now? It takes a little bit longer, but you can do it. Such that these people have never existed. These people have never existed. And you can see little artifacts over in the right eye. And if you don't see how if you work in media and you don't see how the capability of generating this in about an hour changes everything, then keep looking, because it will. Right? Like all of the fundamental infrastructures around what is truth and how trust is produced and so on and so on, all of that is about to change in a really massive way. This is by the artist Trevor Paglen. This is just training a data set on the images in Freud's interpretation of dreams, and saying, just come up with whatever, just keep going until it looks real. And this notion of the GAN, it really comes back to what I was showing you earlier, which is that you need something that's generating an attack, which is in this case the artist who's built the chalk, and then a discriminator that's looking to figure out what's happening about that. And this is real. This happens all the time. So in this particular case, this truck serves as the generator, and this is the car that was unable to discriminate it. Okay, so this was the first fatal accident involving a self-driving car a couple years ago, and in which the car was looking for open sky, and it looked more looked more like open sky than it looked like a truck, and so it went into that at about, I don't know, 60 miles an hour. And this idea that there's the generator and there's the discriminator is important because one of those needs to be human for this to work. And every time I give a talk about the risks of opaque computation and executive control, I think, okay, this is going to be the time where there's not an air crash in the news. And that never happens. There's always an air crash in the news. And so we have to talk about airplanes for a second. And I just want to be clear, it's not to say that flying is dangerous, otherwise I wouldn't be here, just that our species really does a lot of it. And it really, the airplane is one of the places where the interaction between humans and machines is at its highest value. And it leads to this notion that Ashwin Parameswaran talked about on a blog post a couple years ago, that people make poor monitors for computers, that the role of a human is not just to watch what a computer does. He said, the disasters that we see, and this may be the case with the latest 737 crashes, or it may not, probable though. This in particular is a crash from many years ago that we're looking at here, but that the disasters are not driven by human error or systems error alone, but by fatal flaws in the interaction between the human intelligence and the complex, nearly opaque systems. And James Reason talks about it, that these complex, tightly coupled, and highly dependent systems have become increasingly opaque to the people who manage, maintain, and operate them, and so on. Okay. And you know, if the President of the United States is tweeting about it, you can be sure that this is now either a mainstream topic or the fog of an Adderall daydream. But this is what's happening, which is that even the President is saying, oh, the airplanes are becoming far too complex to fly. Pilots are no longer needed. Now, this is, of course, totally false, because we're way, if you look at the right, we're way, way, way safer than we were before those computers were introduced, right? The answer is not to go back to pilots who know everything about how to work the plane, and they're exhausted, and maybe they're having a bad day, and who knows. Like, that was actually one of the worst ideas ever. And so the alternative to what we've been looking at is not that one proposed by the President of the United States, but rather something a little bit more elaborate, maybe a little bit more subtle. This is from a friend of mine, Ari Gesher at Palantir, who talks about so this is referencing Garry Kasparov, the chess player and politician, well, the chess player, and writer and philosopher, who was talking about what happened to chess. So in 2005, chess had collapsed because nobody could tell when they were playing online whether they were playing against a human or against a robot. And that's not really that fun, and it makes competition impossible. And so finally, in 2005, they said, okay, you know what? Whatever, we'll just let anybody bring whatever they want to the table. And so Garry Kasparov, greatest chess player of his time, was talking about that. And he said, okay, so anybody can compete with any other players however they want. But he said, so the thing that wasn't surprising to him, but was surprising to me, and is maybe surprising to you, is that, okay, the best chess player there was totally dominated by even a mediocre machine. Okay, the best chess player in any environment is dominated by a machine. However, the best machine was totally dominated by a mid-level grandmaster playing together with a mid-level machine. But who won the tournament? Two Americans working with basically, I forget if it was like 3 or 9 laptops in front of them. That's who won. Two guys who basically barely knew how to play chess, but what they knew how to do was how to navigate a heterogeneous set of machine opinions that were presented in front of them. They knew how to do what the people who were predicting the weather didn't know how to do, which is not to look at the output of one machine, but to look at a whole bunch of opinions, including their own, including their colleague, including all the ones in front of them, and arrive at some consensus that this is what humans are good at. This is what we're special at. And it's a notion of what we call not artificial intelligence, but rather extended intelligence. That what the machine is there to do is to produce a different set of opinions, not the definitive opinion, a different set of opinions, such that we can negotiate those in our own thoughts. I think about this as our daughter is sort of coming online, which is to figure out, where does intelligence reside? If she was raised in a black box somewhere with no input, she wouldn't become smart, right? What intelligence is essentially a social function. What intelligence is essentially taking heterogeneous, disparate, sometimes contentious ideas, bringing them together and figuring out how to navigate those. And that's, you know, this notion of intelligence as a fundamentally distributed phenomenon, sort of the way that we need to start building these machines and ideas, to design for the intelligence of ecosystems rather than individual intelligent minds. This is some work that I did at MIT around chess, which we don't have time to get into. But we need humans to help, because the algorithm is inscrutable. Even the algorithm that is looking for the human mind. So this, what I showed you earlier, the machine learning that's trying to figure out all the neurons in the brain, ended up having to build essentially a game so that people could help it not make as many errors, right? It can get you 95% of the way there, but that last 5% is something that only humans can do, and that will always be the case. And the most important part is that it will always be about negotiating between those two. You can see this in Spotify, and this overall notion is called human in the loop, right? And this is a way of thinking about and building machine learning such that the things that are happening in the machine have some legibility to the people who are working with them. And I'll just give you, I have a couple examples, but we only have time for one. So this is Karthik Dinakar, who's a close friend and colleague at the Media Lab. This is the best example of human in the loop computation I know. So there's this interesting problem in most cultures, which is that it's been studied over many years that when there's a cardiac event, a heart attack, a stroke, any kind of something like that, women suffer far greater consequences than men. And for years, there were tens of millions of dollars were poured into looking into the physiological basis for why, when a woman has a heart attack, why is it so much worse for them? And the answer turned out to be there is no physiological reason for it. The answer turned out to be hospitals. The answer turned out to be that women talk about pain differently than men. And if you've ever been a woman or a man, you know that, right? Like, you know that, and you probably have some reasons about why. And what happens is that we have generations of doctors who have been trained on bad data. The generations of doctors who have been trained on how to listen to symptoms as they are described by men. And so what happened over decades was that women were misdiagnosed or underdiagnosed or diagnosed too late, and their mortality rates were significantly off. So the question is, how do you attack that problem? And the answer is to basically say, okay, a machine could easily tell that a woman is having a heart attack. Much, much better than any doctor out there. But nobody's going to bring their heart attack to a machine. I doubt it. Like, I think in all of everything that humans have in front of us, I don't think we're ever going to go to a robot in the middle of a heart attack. We're still going to go to a doctor. But then the question is, who's right? Right? Like, how is that going to work? And so the way that this is being deployed in a hospital in Massachusetts is that the doctor is still doing the diagnosis, but there's an AI that's basically listening, much like Alexa, and when it hears that it's a woman, and when it hears that it's a heart attack, it pages the doctor and says, just check it again. And that is a system that is designed, to my mind, correctly, right? That this is what it's to say that the doctor has an opinion, the machine has an opinion, and now the doctor has to figure out who's right. And I mean, you could come up with hundreds or thousands of examples. Flying an airplane is one of them. But most of the systems that are being built are not being built like this. This is the model. And there are other examples, but we don't have time. So anyway, I'll just leave on this note, on this heartwarming note. Some of you who might follow such things might have noted that chess got beat by machines a long time ago, but Go, the game of Go, was thought to be unsolvable, and then basically a machine beat Lee Sedol last year, maybe 2 years ago, the best Go player in the world, and like years ahead of schedule. Now, the thing that's interesting is that this isn't Lee. I forget this player's name. This is the best Go player in Europe, and what he was sort of, the machine sort of trained on him, and he was the best Go player in Europe. He fell to the machine, but the thing that was crazy is that afterwards his game was so much better. And why? Because the machine didn't play like any human had ever played in the history of Go, which is several thousand years. Like, the machine played differently than it had ever played before, and it brought to him a new way of seeing and thinking the game that he was playing. So Go doesn't go away. It's still a way that humans can interact in a meaningful way and in a beautiful and lovely way. But now we can do that in a way that we could never have done it even without the machine there. So what the machine can do is not do the computation, but to actually change the way that we see the world. And that, I think, is its greatest value. So with that, I hope everybody is here to extend intelligence and not to replace it, and have a good day. So, thank you.
Thank you, Kevin. May I request you to use this mic? There's a little disturbance with your mic for the Q&A. You can keep wearing that. All right, let me bring up some of the questions that are coming in. I like this question for its very base fundamental concern. It comes from Anjali. She doesn't give us her company name. Let's assume she works in marketing, and the question is simple: will I lose my job to a machine?
Well, I don't know you.
Anjali, what do you do? If you're in the hall, just yell it out. What do you do? Graphic design? Branding? Right.
No.
Is she going to lose her job to a sophisticated algorithm that can create branding?
I think that the place where machines are going to move the fastest and furthest in the creative industries is really at I grew up as a designer and then an art director and a creative director, and my early years were spent basically doing like a lot of variations, and that's the role of any junior person, is basically try out 5 different things of that. That's something that a machine can do way better and way faster and way cheaper, and can probably generate new ones that maybe that junior designer couldn't have done. It's also true the junior designer would do some there. But I think the ability to generate many variations of something, which has always been the general junior role, I think that is going to go away very quickly. And that will break a lot of the overall structures by which a lot of branding, marketing, and advertising gets made in ways that we can't quite predict. I think at the middle and the top, it is still anybody who's still in the role of synthesizing different opinions, that will become more valuable as some of those opinions become the ones that are from machines.
Right, so his advice to you is don't be junior.
Right.
If you must work in branding, be senior.
Right, yeah.
Get
up
the value chain quickly.
Yeah. Sure, that's the short answer.
We are running out of time, so I'm going to summarize a bunch of other questions we're getting. All of them ask the same thing, and all of them have watched the Terminator and Minority Report, is when is the technological singularity going to happen? For those of you who don't know what a technological singularity is when a machine becomes self-aware that it's a machine and acquires a consciousness and the ability to build other machines or to make independent decisions. Assuming that you're not a robot, Kevin, when is the technological singularity going to happen?
Yeah, everybody has a different opinion on this. My opinion is never. My opinion is that that's not, the kinds of machines that we are building are not what are called GAI, general artificial intelligence. It's not a goal. It's not where the money is. It's also broadly. I'm not going to say that it's impossible, but we're nowhere close by anybody. Let me put it this way: there are people who work with machines who think that we're close, but anybody who works with brains feels like we're pretty far. So, yeah.
All right, so you're safe for about 100 years, and after that, it's anybody's guess. Kevin, thank you very much for joining us.
Thanks to all of you.
Sorry, we can't take any more questions. We are running out of time.